Hi everyone, family duties call. So here's a video of 8.4 intersections of lines in 2-space and 3-space. Now, considering it's a video, I know a lot of you are probably more itching to study for your mini test tomorrow. That's Friday. It is still on, which means any questions you might have that you wanted to ask today, send them to me by email or ask friends. Be resourceful in answering them. I will do my best to respond to your emails, but it is what it is. Be as resourceful as you can. Okay, I'll make this video as short as I can, but I do want to go through them very clearly because I think it's important. Intersection of lines in 2-space or in 3-space essentially is a system of lines. If you remember in grade 10, you were introduced to two lines and you have to find a point of intersection. Because it's 3D, more situations arise. Okay, so in grade 10, you might have seen 3 different situations. In grade 12, there are 4 different situations you ought to be aware of. Okay, I will draw some parallels, no pun intended, with what you learned in grade 10 versus what you see now, and also talk about the differences. Okay, the concept itself is fairly straightforward, but I want you to see it in action and show how each of these scenarios would show up algebraically or even geometrically in solving a question. We will do example 1 and example 2 together. I'd like you to try example 3 and 4 on your own, and I will provide a separate video solution of 3 and 4 on the Brightspace. Okay? Example 5 is particularly special, particularly important. And so I am going to save this for Monday. Leave for Monday. Now, that might be bad news for some of you because I know I'm gonna sound so annoyed by this, but I'm not pulling my hair. I am a little bit, may I say, mildly infuriated. Okay, but I know Monday is your how do I word this? Grade 12 senior, I am entitled to this because it's tradition, I'm not coming to school day. And so it's just one concept. If you choose to skip on the Monday, you will be missing out on this. It will be your responsibility to ask a friend who might have shown up or learn this on your own by reading it. Look at the notes on Brightspace, maybe use a textbook, but the concept is the shortest distance between two lines, essentially the skew lines, is actually a projection. It's a dot product, basically. Okay, so there it is. But stay tuned. Hopefully you will come on Monday, or you know what, if it's really bad, maybe I'll just make a video. I don't know. We'll figure it out. Without further ado, let's get into it. Lines. When you were talking about lines in 2D, where is my blank? Okay. When you're talking about lines in 2D, you had 3 different scenarios. You had a line and a line. And so you had a point of intersection. You could also have a line with another parallel line, and they would never intersect, so therefore there is no solution, no point of intersection. Or, lastly, you could have a coincident line. So literally, they have the same slope and they have the same y-intercept. They just are written differently. Like, for example, you could have had 2x plus 4y minus 7 equals 0. And then the other line was 4x plus 8y minus 14 equals 0. They're essentially the same line because they have the same slope, same y-intercept, and so they are what we call coincident. Excuse my terrible writing. Okay? So that is the exact same in 3D. You could have 2 line or, vector equations that have a single point of intersection, so one solution. We could have 2 lines that have the same direction vector and they both have a position vector that lands them on the same line, and so there are infinite solutions. They could be perfectly parallel, so their direction vectors are perfectly parallel, and so there's no solution. And here, because it's 3D, we have a new scenario where they are skew lines. What do I mean by that? Because they're 3D, you have to consider a situation where we have, let's pretend we have a line going this way. Okay. And being 3D, you don't think much of it. It's just 1, 2, 3. We could also have a line that is, I'm going to see if I could do this. I need a thinner line. I'm not sure if you see what I'm trying to do here. Do you see what I'm trying to do? I'm trying to draw a 3D line, and so the line is actually coming closer to us and going further away. If you notice, this line that I'm trying to do is not actually crossing. It is a certain distance away. Okay, there is a gap between the two. Okay, so if I were to draw it 3D, maybe this thing casts a shadow. Maybe this thing, I can draw it casting a shadow, and it's like right here. Right? So it's not that they're intersecting here. It's actually casting a shadow, so there is a fair distance between them. You get what I'm saying? So if you think about it, are their direction vectors parallel? No. Do they have, any kind of common intersection? That's also a no. Okay, so normally if you have two lines that have different direction vectors, you think, oh, they have to cross. Not in 3D. One is up here, the other one is down here. Okay, so there is a space between them. That is what we call skew lines, and there is no solution. Okay, I hope I made that clear. It would be nicer if I was in front of you and we were drawing, if I was using meter sticks. Okay, but I guess we'll have to say that until I come back. So those are the three situations, and that's the lesson. But once again, if you have those three, how does it show up? There's a couple of things that we need to be aware of. Number one, because they are lines, we could talk about, and they have a specific direction vector, we could use, I'm going to say normals. Right? Depending on if it's 2D or 3D. If it's 2D, I can use normals to our advantage. If it's 3D, it's a little bit harder. Okay? So, how about I specify? In 2D, we can have these three. If it's in 3D, we could have all three of these plus that one. Okay? So when you see this line, for example, this would be clearly two lines in a 2D system. We only have to worry about these three situations. Let's see how this applies, or how we can analyze it algebraically and geometrically using vectors. Okay, so here we go. Determine the number of solutions, 1, 0, or infinite. 0, 1, or infinite for this linear system. I like blue. Let's do blue. Using an algebraic substitution. Okay, so let's go grade 10. We have 4x minus 6y equals negative 10. I have 6x minus 9y equals negative 15. Nothing to eliminate there. So how about multiplying the top one by 3, multiplying the bottom one by 2? I have 12x minus 18y equals negative 30. I have 12x minus 18y equals negative 30. Oh, wait a minute. Wait a minute. What do you notice? So because 12x and 12x are the same, I am going to subtract the top equation with the bottom equation. But what we get is a 0 minus a 0 equals a 0. What does that mean? By default, let me make this text a little bit bigger. How about I do 15? Any x and y value satisfies the system. In other words, x could be 1,000,000, y could be 1,000,000,000. It still works. X could be 0, y could be 9,000. It still works. X could be a negative 0.115, y could be whatever. It works. In other words, there is infinite solutions. And that's how it looks. Okay, so this would be a case of that one right there. The two lines are exactly on top of each other. So that's an algebraic substitution. You know how that works. What if we analyze it geometrically? Is there a way we can solve this without even having to go about this? Like, where does the grade 12 aspect come from? Consider this. If we are talking about this as a Cartesian equation or a scalar equation of lines. Right? Like, so vectors. Using vectors, we did the parametric equations, turning it into symmetric, turning it into a scalar. What does the coefficient of x and the coefficient of y tell you about this line? If you remember from your practice, the normal of this line, so I'll call it line 1, the normal of line 1 is 4, -6. The coefficients correspond to the normal. What do I mean by that? What I mean by that is, if this was my line, my normal, I'm going to assume that's about 90 degrees. My normal vector is 4, -6. Okay? What about this one? The normal of the second line is 6, -9. Right? And so, again, I don't know what this line is, but I do know that the normal is 6, -9. And at this point, you should see the numbers. You should notice it. 4, -6 is a scalar multiple of 6, -9. Right? So you can say, if I take 4, -6, multiply by 1.5, multiply by 1.5, 3/2 times the normal would be equal to normal 2. What does that mean? If the normals are the same, or normals are essentially collinear, then the direction vectors are also collinear. So I can say line 1 is parallel to line 2. There is a analysis right there using just the normals. What does that mean? Well, I haven't fully completed it yet, but now we test. Okay, if this is true, how about I take 3/2 and multiply with 4x minus 6y plus 10. Do I get the same thing? I get 12/2, 6x, 18/2, -9y, 30/2, plus 15 equals 0. This is line 2. So I can argue, hey, 3/2 times line 1 equals line 2. They are coincident. Right? So there's infinite solutions. So there's a lot of different ways you can go about it. Obviously, I did more writing and more thinking with the right side than the left side. However, there are certain situations where your analysis really just comes together so nicely that you may want to keep that in your back pocket. So let's do exercise 2. That's another example. This one is an example of having no solutions. Okay, so they are going to be parallel to each other, but there are no solutions. Notice here, it says algebraic substitution, but I'm going to add, you can obviously eliminate as well. So here, determine the number of solutions for this linear system, algebraic substitution or elimination. And this time I give you vector equations. All right, let's do it. Seeing as how you could change this into scalar equations, like so, there's nothing stopping you from doing it and continuing on with grade 10 style calculations. I am going to try to use vectors and apply grade 12 methods. How do I do that? Remember, line number 1, if they gave it to you as a vector equation, I can always rewrite it as parametric. And parametric is so useful. I highly recommend it. Okay, next, line 2 would be x equals 2 plus 9t and y equals 1 minus 12t. Yes, the parameters are different, obviously. Here we go. If they are going to intersect, maybe I should write this down. If there is a solution, then at some point, x of line 1 equals x of line 2. Right? It's got to. And then, of course, y of line 1 equals y of line 2. So I'm going to do that. So if that's the case, therefore, x from L1 equals x of L2. In the same breath, y from L1 equals y of L2. You see where I'm going with this? I have two equations with two variables. So let's rearrange. I could do elimination, but yeah, you know what? Elimination I think is easier. The coefficients of s and t don't look very pretty. So let's do it. I've got 1, subtract 2 from both sides, -1 equals positive 6s plus 9t. Subtract 1 from both sides. No, how about I bring this? This becomes 8s plus 12t equals a -4. There it is. So we have 6, 9, 8, 12 with corresponding variable numbers. Okay, so I'm bringing these together. I will start here, elimination. S and S, is it easier? I think it would be easier to make both of these 24. So multiply by 4, multiply by 4, multiply by 4. Here, multiply by 3, multiply by 3, multiply by 3, multiply by 3. Okay, I already see something not good is going to happen. Since the variables are the same, I'm going to subtract top to bottom. -4 minus -12 is 8. Then we've got 0 s plus 0t. So in what world will you have 8 equals 0? Right? Nothing. Never. Therefore, no solution. In other words, they both have the same direction vector, but they are distinct from each other. No solutions. Is there an easy way to come to this conclusion by analyzing their vectors? Well, maybe. Part B. Because they give you the direction vectors, you can immediately look at not the normals, but the direction vectors themselves. And you will see that, oh, wait a minute. Is -6, 8 a scalar multiple of 9, -12? Well, we can try it. What do I have to do to multiply 9 to get to a -12? Well, it's -6 equals k times 9. k equals negative 2 over 3. And 8, does that negative 2 over 3 work? Negative 2 over 3 times negative 12 is negative 24 over 3. It is, positive, so it is an 8. Oh, it checks out. Ooh, that means the direction vector of 1 is the same, or rather, parallel to direction vector 2. What does that mean? That means line 1 is parallel to line 2. So what are our options? That means we could be either infinite or 0 solutions. So how do we check? Those are the only options. In other words, there's infinite number of points meeting each other, or there's going to be none. So what you're going to do is choose a number. You can say, hey, if they are the same, then 1, 5 should be found in L2. Or in flip, 2, 1 should be found in L1. If 2, 1 cannot be found in L1, then they are not the same line. That's it. So I'm going to do 2, 1 just because it's smaller in value. I'm going to say, hey, the x value from line 1, my x value is negative 1 minus 6s. Right? If my x is 2, what does s have to be? Let's see. 2 minus 1 on both sides. I have 1 equals negative 6s. S equals negative 1 over 6. Ooh, not the best number, but that's okay. Let's plug that into my y. Y is 5 plus 8 times s. 5 minus 4 over 3, 4, 3, and 2 over 3. That is 11 over 3. It's supposed to be a y value of 1. It is not a y value of 1. Right? So it is parallel, but there is no point common between the two, so we know it is no solution. They are distinct. Okay? And that's it. So I'd like you to be comfortable looking at how lines could be done in grade 10, or in system of lines, system of, I guess, linear equation can also be solved by analyzing them. Okay, using their direction vectors or their normals. Would you please try example 3 and example 4 on your own, just to give you a heads up of what it is. These two lines are going to be parallel but distinct. In other words, it's going to be exactly the same as example 2. And then example 4, I believe the two are going to be, let's see. For part A, there is going to be one solution. And for part B, they are going to be what we call skew. Okay, let's try it. I really do encourage you to try it. Example 3 and 4, we are going into lines in 3D. As you can see, it's X, Y, and Z. But the kind of work you do, the analysis that you do, the elimination substitution that you do, does not change. Okay, so do what you can. Look at the other video if you want a full solution. And this is going to be Monday. Okay, and that's it. Please spend this class time truly working on these. Do your very best to find full solutions. Even if you can't, discuss with your partners, discuss with your elbow mates, discuss it with whoever, and solve it. And then use whatever devices you have to check Brightspace. Okay, I want you to struggle. I hope you really spend this time wisely, and I will see you on the mini test day, Friday. Okay, bye.